Hello everybody, welcome to another episode of Mankind in Training. Sorry I've been away for so long. Today we are doing the long-awaited question and answer video. We got quite a few questions, so I'm not going to be able to get to all of them today, but because the ones that I've chosen are going to take up most of my time. So if you paid to get a question answered and I didn't get to it, we will get around to it in the next one. I am back. Like I said, sorry I was gone for so long. We will be back and making more videos again and on a regular basis. Today we got quite a few questions about math and science. Now, I am not a math major. I'm a computer science major, but I will do my best to explain what I do know. And now we will be getting on with it. Behind me, I have my handy dandy whiteboard, and we will begin. So, the questions are. Oh no, we'll get to that at the end. I'll just explain everything, and then you'll know that I answered your question. But I will read off your names and the questions that you asked at the end of the episode. So. Today we have E, an irrational number. We have the root 2, another irrational number. Gelfand's constant, another irrational number. We have pi. I'm going to explain complex numbers or imaginary numbers. I'm going to explain vectors and tensors. And then I'm going to get to the black hole question. So to begin, Euler's constant is extraordinarily important in mathematics. It is the language of growth. And if you try to do anything, if you intentionally try not to use Euler's number, you're just making everything a lot more difficult for yourself. So what Euler's number is regularly, you'll see it as E. And the formula for E is 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus ... 1 over n factorial out to infinity. And that's what makes it an irrational number, is that it just continues on forever. So once you plug in this formula, you get E equals 2.718288282459045223, and so on and so forth. Now, I is another question we got, and I'm going to do my best to explain complex or imaginary numbers. Now, I is the square root of -1, and we're going to get to e to the I pi. So here I have e to the I pi plus 1 equals 0, and that is commonly voted as the most elegant equation in mathematics. So now we're getting on to Gelfand's constant, or Hilbert's number, as it's also called, which you can get by 2 to the power of root 2, or e to the pi, e to the power of pi. And that number is 2.665144142690, and so on and so forth forever. Again, another irrational number. So here I have root 2. If you have a triangle with side lengths of 1 and 1, the long side will be root 2. And root 2 is 1.41421356237, and so on and so forth. We have a whole bunch of irrational numbers today. A real fun one is this. I always thought this didn't make any sense until it was explained to me a lot better. 0 factorial equals 1. What? I always thought that was nuts. How is 0 factorial equal to 1? Well, I'll explain it somewhat. So what a factorial is, we had it here in Euler's constant. A factorial is, so if you have 5 factorials, say, that is 5 times 4 times 3 times 2 times 1, and that is equivalent to 120. So what we're going to do is we're going to break down all the way down, and I'll explain how 0 factorial is equal to 1. So if you take 5 factorial, 120, and divide it by 5, you get 24. And then if you go down further, we have 4 factorial divided by 4 equals 6. And 3 factorial divided by 3 equals 2. And 2 factorial divided by 2 equals 1. And then 1 factorial divided by 1 equals 1, which brings us, and that is 0 factorial. Nextly, we have Gelfand's constant again, and that is given by E, which we've went over, is 2.7182181 to the power of pi, which is 3.1415, so on and so forth. It's an irrational number to the power of an irrational number. Now, the reason this is important, there's several reasons, and we're going to bring it all the way down to wave mechanics in quantum physics. So E is just such a beautiful number, and it's used constantly, and so is pi. So e to the pi is approximately 1 plus 1 over n to the power of n times pi. And then, so 1 plus pi over n times pi to the power of n times pi. So if you take E as the perfect compounding growth, this is an approximation of E. This is E, and then this is this right here, the e to the x, is approximately 1 plus x over m to the power of m. And then as you increase, like, so with m as 1, it plots out to something like this, the bottom line. Now, as you increase m, you get closer and closer to the e. And then you get, as m approaches infinity, the higher your m, the more closely approximate to e you will be. So e to the I pi, which you'll see, e to the I pi, I did that up here, e to the I pi plus 1 equals 0. And we're going to break down to here. Now e to the I pi is equal to negative 1. And it's very simple to do so. You take, because e to the I pi plus 1 equals 0, you just subtract 1 from both sides of the equation, and you get negative 1. So, where was I at here? E to the I pi is important, and you'll see it all over the place. It's used frequently in mathematics. So now we're going to get to imaginary or complex numbers. This is the unit circle. Now this is the real number line. 1, 2, 1, 2, 3, 4, out to infinity in both directions. Now, you take and make a different plane. So in this case, we're using the imaginary plane in the y-axis, but it's not the y-axis, it's the imaginary plane axis. Technically, the y-axis would be like out here. It'd be up like that. So I'm going to explain the unit circle here. So if you take and multiply 1 times I, you get I. And if you take I times I, by definition is -1. And if you take -1 times I, you get -I. And if you take -I times 1, you get 1. And it just completes this circle here. Now, you'll see why this is important. I'll show you down here with the wave mechanics. So I'm going to do a quick explanation again of the imaginary and the real number line. So here we have just a plot where I have my real number line axis again here, and what you were used to seeing as the y-axis as the imaginary number line. So to get a complex number, you have a real part and an imaginary part. So here I have, if you take and plot this dot here, that would be 2 plus I. You go across 2 on the real number line, and it has 1 imaginary component. Now, this dot here that I plotted, I drew triangles and then rectangles up to them. So this has 1 part of the real number line, and then 2I on the imaginary number line, so it's 1 plus 2I. And both of those are complex or imaginary numbers mixed with a real component. So here we have this unit circle, like I was saying earlier. If you take a function that continuously multiplies by I across the real number line or across the imaginary number line, where you're constantly multiplying, you get, so e to the ix is this function. Now, if I take this real number line and this imaginary number line, and then this would be like the y-axis, I've made this into a 3-dimensional kind of a plot. E to the ix will continuously spiral around the imaginary number line all the way up and down, and e to the ix on the real number line will constantly spiral around the real number line on a plot. Now, if you take this 3-dimensional plot and turn it so all you're seeing is a 2-dimensional representation of that 3-dimensional plot, this is really cool. The real number line here, if you look at it just from a 2-dimensional viewpoint, it gives you the cosine wave. And if you turn the plot again, so you're looking at it at the side of the imaginary number line, it will give you the sine wave. How cool is that? You get trigonometric functions out of imaginary numbers. Now, the sine and the cosine wave are extremely important. They're used all over the place, and they're important, and e to the I whatever, e to the I pi, e to the ix, these functions were used by Schrödinger when he devised wave mechanics. So here I have Schrödinger's equation, which is psi of x and t, which is the function psi of x and time, equals a e to the I k x minus omega t. Now, the cool thing about this is if you take the partial derivative with respect to time, which is here, the partial derivative with respect to time, of the function psi of x and t, it's equivalent to negative I omega a e to the I k x minus omega t, which is proportional to negative I omega psi of x and t. It's proportional to itself, and that's one of the most beautiful things I've ever seen. Schrödinger's equation and wave mechanics describe, it's amazing that nature uses imaginary numbers. they describe everything that you see, touch, feel, even the particles in yourself, the things that you are made of, the things that everything is made of. Everything's all a jumbled soup of waves. It's only until it's observed that we can see point particles. So once you become entangled with the particle that's in, like, I like to think about it like this. The entire universe in the timeline that we're trapped in, it's all one big wave function. It's all a series of amplitudes colliding together. We're all trapped in the wave function, and that we're all entangled together. Everything in the entire universe is entangled at some level, and that's what keeps us all together in this space and time. It's a beautiful thing. So now we're going to get onto basis vectors. I'm going to explain what a vector is, and I'm going to explain what a tensor is. And a tensor is just, okay, so a vector is a tensor of rank 1. So this here, I have a plot. This is the y-axis, this is the x-axis, as you typically see. A vector is just a directionality and a magnitude. It is something that is, you can think of it as an arrow, and it has some magnitude. So this vector here is made of basis vectors, or made of base components. So 1, 2, 3, 4x and 1, 2, y. 4x and 2y make up this basis vector. And then I have a second vector here, so this is a 2 vector that I have displayed here, but you can just think of them as 2 individual vectors if you like, if it makes it easier to understand. This second vector has components of 2x and 3y. And then you can think about the vector as these are a sub x, both of these, the coefficient and x. That's a sub x. And then this is a sub y, the coefficient and y. Now, a tensor is made up of a series of vectors. So this would be, forget about the cube, just think about this square right here. This is a tensor of rank 2. And what it has is all of the base components that would make up this tensor. So it's a sub xx, a sub xy, a sub xz, a sub yx, a sub yy, a sub yz, a sub zx, a sub zy, and a sub zz. And now if we want to expand upon this and make it a three-dimensional, a cube, if you will, that would be a tensor of rank 3, and then that would have 3 components. This would be a x, x, that would be, you know what I mean, and so on and so forth. A x, x, x. And then this would be like ax, xy, and then ax, xz, and then you would go all around. It would have every bit of all of the components, and that would be a tensor of rank 3. Now, okay, I think I got to most everything. Now we're down to the black hole question. The question was, what is happening with a black hole? I seen a picture of a black hole. I understand that it sucks everything inside of it, but what is going on with a black hole? Can you explain it better? So, I have a poorly drawn black hole here. Inside of this dark area is a singularity. a infinitesimally small point of immense mass. So massive, in fact, that light traveling will get bent into the black hole. Light will get bent into the black hole. Even light out here, that's either normally it would hit something and be absorbed or continue on forever until it hits something and is absorbed or reflected. Now, something that's going on this trajectory still will end up falling into the black hole. There's a certain point where, now I drew that out a little far, but the event horizon is in here. This is the event horizon here. If you cross the event horizon, you will, like she said in the question, you can't escape a black hole. You're going into it. The mass is so great that gravity is unescapable at the point where you make it to the event horizon. If you cross it, you will be going into the singularity. However, it distorts space and time in such a way that it's possible that with everything that it's been sucking in, it could be so massively large in there that it could take forever to get to the singularity. There may be an entire universe inside of the black hole. Now, what you're seeing in the picture, this is called an accretion disk. And this is made up of light and matter that has been sucked into an orbit, and it's spinning uber fast. It's extraordinarily fast. It's been... black holes have a rotation most of the time, and even if they don't, there's still usually an accretion disk. It just won't have... we've measured, like... So, if there's, like, a star here, we've been able to measure the speed of a black hole... Oh, I had it going that way. Sorry. So we've been able to measure the speed of a black hole by seeing an object in the accretion disk and how quickly that it goes, that we see it again in that same spot. Now, there is several parts to the black hole. There's not only the event horizon, there is a spot inside of the accretion disk, and it's the final spot that something can be in an orbital around the black hole. There is a point where you can be in a stable orbital around the black hole, or semi-stable, as long as you're not in the event horizon itself. But most everything is just, the trajectory is slowly bringing you towards the event horizon. The cool thing about, well, there's lots of cool things about black holes, but the crazy thing, I should say, about a black hole is, so this accretion disk goes around to the backside of the black hole, and this halo around the top and the bottom, it's not there. What you're actually seeing is the backside of this accretion disk. And it's being folded up and folded down by the immense gravitational pull. So it's distorting space-time in such a way where you're seeing the front and the back of the black hole at the same time. And it's said that it's the holographic principle is saying that the information and the energy stored in this accretion disk, even if it makes it into the black hole and is sucked into the singularity, slowly but surely, energy is being evaporated out of the black hole, and it's called Hawking radiation. And it's been proven that the information and the energy is not destroyed so much as it's just maybe recycled. It's turned into something, it's broken down into its component parts, and as the black hole slowly evaporates and gets smaller and smaller, eventually all of the information is released back out into the universe. Maybe not, and this is we still don't know a lot about black holes, and I still don't know a lot about black holes, but that's what I've understood about it thus far. Thank you for watching, everybody. I'm going to now read off the questions and the names of those who paid to have them answered. So the first question was by Gerhard, and his question was, what are imaginary numbers? And we covered that, I think, pretty well. 2 was anonymous. It's not, it literally said anonymous, so sorry about your shout out, but I guess that's what you wanted. What is Euler's number? Third question was by a K. Tellinger, who asked, what is e to the I pi? The fourth question was by a Luke DeBoss. He asked what Schrodinger's equation for wave mechanics is. And Kelly R. asked, why is root 2 irrational? And I explained that because it goes on forever. It doesn't ever stop. It just continues on for infinity. Where were we? Kelly R. asked, why is root 2 irrational? 6 is Steve O 420, which I love your name, Steve O. Why is 0 factorial equal to 1? I loved that question because I had the same question. Next was Marcus D. He's number 7, and he asked, what is a vector and a tensor? And number 8 was Susanna, who asked me about the black hole and what is going on with it. Thank you for watching, everybody. I will be back with another question and answer episode for all the people that I didn't get to today. And then we are going to do probably it's hard to pick what I want to do, but I think we're gonna do a little tutorial on Python. I'm gonna show you something that I'm working on, or maybe we'll do math. Maybe we'll do Wolfram Mathematica, and I'll do a little run through on how powerful that software is. I know I've done a lot with the quantum framework, but I also want to show you all the other cool stuff that Wolfram Mathematica can do. It's such amazing software. If you can afford it, it's only like, well, because I'm a student, I got kind of a discount on it, but if you can afford the software, I think it's only like over $200 or something a year, which really isn't all that much per month. So thank you for watching, everybody, and I will be back with another episode of Mankind in Training.